Hello and welcome to Empowered Learning. This is Unit 1 of a data-driven decision-making course. And so the very first chapter that we cover in this course, we go over the basics of linear programming. And so that's what this particular video will be about. And essentially what we're trying to do here is model situations mathematically, either by hand or to put them in a spreadsheet tool like Microsoft Excel, and from that figure out what our optimum solution will be. And so if you check out the assortment of videos that I'll have, you'll see that we keep with this theme throughout all the videos, as far as modeling a situation mathematically, and then afterwards doing it either by hand or in Microsoft Excel most of the time to be able to come up with some type of optimum solution. And then from that, we interpret things from the solution. So first thing that we're going to talk about here is to actually define what a decision model is and describe the importance of those models. And then we also want to discern in between what is a deterministic model versus a probabilistic model. And then after that, then we want to understand the steps involved in coming up with these decision models in practical situations. Afterwards, we want to understand the basics of using spreadsheets to help us in the decision modeling process. And finally, we want to discuss some possible problems or issues as you develop decision models. And so this may be in a investor setting, business setting, or maybe a personal setting if it's having to do with your family or some type of organization that's involved with your family. So, all right, so what is decision modeling? So it is a scientific approach to managerial decision making. And of course, a lot of things in this world, you'll find that even though there's words to describe it, a better way to describe what's going on without having to say so many words is to model it mathematically. So you'll see a lot of times in most courses that has anything to do with math, they'll tell you the concepts in regular words or whatever language that you speak, but at some point they introduce the math. And so the point of introducing the math is because if you introduce it mathematically, which is in a more abstract sense, you actually say more with less. And so when you're doing decision modeling, often you have to put a situation in math terms so that you can look at it abstractly from a lot of different perspectives. Also, we're modeling real world scenarios here, okay? So we're basically trying to take what we see or what we observe, and we're going to, in turn, make sure that it's expressed mathematically so that we can look at what our options are. And so by doing it mathematically, we also have a chance to change things with ease because the model is so abstract. And so then, of course, decision modeling also provides insight into whatever solutions you have. And so throughout this course, if you're watching the remaining videos I have on this, you'll see how we build on being able to see more and more into our model, interpret more information from our model so that we can make better decisions based upon the model that we have. So in decision modeling, we have two types. We have deterministic and we have probabilistic. For the first couple of units in this course, we will stick to deterministic modeling, which will be, we basically know everything up front, okay? And so since we know everything up front, we can model everything mathematically with exact math like algebra. And from that, we just either do it by hand or we do it in a spreadsheet tool like Microsoft Excel. And we model that, solve the system, and we have our solutions. And then, of course, from those solutions, we will either figure out if we're going to use them or not use them, or we may have to tweak something to make our solutions actually be usable. As we get into The latter part of the course, and if you're taking my course, this will be units 3, unit 4, unit 5, then we turn more to probabilistic solutions where some of the data is uncertain and we're actually using either probability and or statistics to fill in the gap for that. Now, we also have models that are quantitative as well as qualitative. So quantitative models are just ones where they're numbers heavy, whereas qualitative models aren't necessarily filled with a lot of numbers in it, okay? But those models are still important, okay? And they're still important because they have factors in it that can't be quantified. So for instance, just to kind of give you an example. So let's say we're trying to model a situation about introducing a product to a particular market, okay? Well, there may be some factors about that market that can't necessarily be quantified. And so if the person or organization that's over this decision knows some subjective things about the market that can't necessarily be quantified into numbers, um, that is something that maybe you want to include in your analysis of trying to figure out if you're going to launch this new product in this market, and if you do, how you actually launch it. Okay. And so we can also use those decisions or those qualitative type models within a quantitative type model to be able to um, do your decision making. Okay. So of course, with these models, we're eventually going to use spreadsheets uh, to put our models in, because there's going to be a point to where trying to model something and solve the systems that are involved with it from a math standpoint just get too tedious to do it by hand. We will start off in this video doing some simple models where we actually do it in Microsoft Excel. But you're going to learn as you see towards the end of this particular video where I do stuff by hand, anything that's pretty much beyond what I'm trying to do by hand in this particular video will be a little bit too tedious to handle in most cases. That's why we use spreadsheet applications like Microsoft Excel to model and find our solutions without us having to all do the number crunching by hand. All right, so the steps in decision modeling. So the first thing that we do is we do the formulation of it. So in other words, we want to basically understand what it is that we want from our particular model. And then we know that we need to express that mathematically, okay? So let's say, again, if our goal is to bring a product to market, then we need to know what are going to be, what's going to be our profit for it. Do we have any constraints that are involved that's going to either help us or hinder us from making that profit? What does our supply look like as far as the materials that we need to buy to be able to even make this product? What do we know we can sell it for on a particular market? What is the number of potential people or organizations that we can sell this product to? So all those things we need to know about, and that is in the formulation process. So the next thing is, after we formulate our model and we test it out, then of course, second part of it is just finding what the solution is, okay? And then the third part will be interpretation and sensitivity analysis. And so we will get into the sensitivity analysis part of it in Unit 3. And what sensitivity analysis is now that we have an optimum solution for the variables that we're solving for, in order to get our optimum solution, we need to know within what range of our various constraints that we have do those particular variables or values for our solution actually apply. And so with sensitivity analysis, not only can we know the range in which that optimum solution would be true, if we wanted to change one or two things to our situation, we could use sensitivity analysis to be able to analyze and figure out how those changes are going to affect whatever it is that we're trying to measure without us necessarily having to run the model again or change values in the model again and rerun it to get new solutions. So what we could do is use the same model and just from that extrapolate whatever information that we need to figure out what those changes are. Now, as far as the interpretation is concerned, of course, once we have our solution, then it'll be pretty easy to interpret what it is or what it is that we're trying to find, because we would define that in the formulation process of what it is that we're looking for. And so normally you'll know how much of whatever it is that you need to buy, consume, or whatever to be able to reach your goal. So in most instances, that's what the interpretation will be. Again, the sensitivity analysis is just looking over the ranges on which that optimum solution is valid, and from that being able to ask other questions about your model to see if we ask those questions, which may change one or two things, how that's actually going to change our optimum solution. So if we look at this in sort of a block diagram flowchart way, then we see that with the formulation, we're defining a problem, we're developing a model, we're acquiring all of our data. In the solution part of it, we develop the solution and we test the solution. And of course, if we find that there are some bugs or some kinks or some things that we forgot, then we need to go back to the formulation process, develop the model, and do it again. And of course, this is cyclical, meaning that there may be several iterations of that until we get to a model and a solution that is acceptable. And then, of course, after that, then we will analyze the results, do some sensitivity analysis on it to ask questions about our results. And then if we accept everything, in most instances, we will want to implement those results. So now for our first example, we'll talk about a tax computation example where we have a husband and a wife. They both are self-employed and they're trying to see how much they need to pay in taxes. And so we have the following information about their financial situation, and this is going to help us to understand how much they actually need to pay in taxes quarterly. So we start off by knowing that they have dedicated 5% of their money that they make in a retirement account. And of course, at the year that they're doing this, the max that they're allowed to do is going to be $6,000 per what the government sets for that. They also have personal exemptions of $3,700 each. And of course, you can see that, I guess, for whatever particular year that they are in, since they're self-employed, they would have those personal exemptions, and you'll know that by looking at your tax return forms. We also know that there is a standard deduction for married couples filing jointly, and that will be $11,600. And depending upon how much money they make, they may be in a certain tax bracket. And of course, here in America, we know that we have a graduated tax rate. So, of course, the higher you go, you pay a minimum amount plus a certain percentage of whatever tax bracket that you're in. Okay, and so we know that for the 10% tax bracket, that falls in between everyone that is making from $0 to $17,000. The 15% tax bracket for everyone who makes $17,001 to $69,000 a year, and then a 25% tax bracket will be from $69,001 to $139,350. So this is the information that we have. So if we were to model this, this is how it would look. in Microsoft Excel. And so we have all of our known parameters up here. And so you see how we have the retirement savings, maximum amount of savings in, I guess it would be some type of IRA account or something like that. We also have personal exemptions, standard deductions, and here are our tax rates. So we have all that laid out here. Now, what's in yellow right here is going to be what, in this case, Sue's and Rob's estimated income is going to be. So based upon how much money they make, that's going to let us know what everything else is going to be. Now, when we look down here, we're going to see all the stuff that we need to calculate to be able to come to our result, which is how much tax do they have to pay per quarter, okay? And so since these two people are self-employed, they're not like normal people who have full-time jobs. They have to pay their taxes quarterly because there's not enough or not anything being taken out of their checks whenever they get paid, because of course they may be getting paid on contract. So their income is filed probably on a 1099 form versus a W-2 form, okay? So if you're working and your taxes, or I guess your income is made or reported on a W-2 form, then in those cases, you're already having taxes taken out before you even see the rest of your money. Whereas as a self-employed person, it's more like a small business. They're seeing the money first, spending it on whatever expenses or whatnot, and then from there, the rest is looked at as profit. So because of that, they have to pay their taxes quarterly to make sure that the government basically doesn't come after them, okay? So anyway, we have a total income here. And our total income is going to be the sum of B13 and B14. And here, this is the cell B13. And we know that because this is the B, and that's the 13, and it's the cross section in between the two, okay? So here's the cross section in between B and the 13. So that's how we know that. And of course, this is B14. So whatever numbers we put in here, they're being added up. And for those of you that are not familiar with Excel, you see the equal sign that's there. Whenever we type in a formula, we always start with an equal sign. And that lets Microsoft Excel know that, hey, we're about to come up with some formula to calculate something, okay? Now, the retirement savings, we see that we have the equal sign, then we have this thing min right here. And what that is, that's called the minimum function. And what the minimum function is doing is, and I'll just kind of write something right here to make my point. Let's get rid of that. So the minimum function, what it's going to do, it's going to say, what I want is the minimum value in between, in this case, A and B. So let me make sure I get this working correctly. So I want the minimum in between whatever value A is and whatever value B is. In this case, I want the minimum in between what B4 times B17 is. If you look at B4, that is the 5% that I'm saving of all my income. B17 is this cell right here. So I want the minimum in between 5% of whatever it is both Sue and Rob make together and what B5 is, which is the $6,000 allowed by the government. So for instance, if Sue and Rob together, let's say make $100,000, okay? So if they make that, then 5% of $100,000 is going to be, $5,000, okay? So that would work. So in that instance, if Sue and Rob both made $100,000 a year, then of course they will be contributing $5,000 into their retirement savings account. Now, according to what we see here, with cell B18 talking about the minimum of B4 times B17 and B5, we know that B4 times B17 is going to be the 5,000, and we know that B5 is going to be the 6,000. So we're going to take the minimum of those two, which is going to be the 5,000, and that's what we put into the retirement savings. Now, on the other hand, let's say they make $200,000 a year together. So, of course, we know 10% of 200,000 is 20,000. So 5% of that would be half of the 20, which would be $10,000. And so in this case, we see that the minimum value is the 6,000 that the government said that you can save no more than that in this particular account. So even though they would want to dedicate up to $10,000 in retirement savings, the government is only going to give them a write-off for up to 6. Okay, and so that's what cell B18 talks about. All right, so moving on here, we've talked about cell B17, B18. Now for B19, these are the personal exemptions. And of course, B6 tells us what the personal exemption is for each person. You see that there. And of course, you see that we have the equal sign, then it's 2 times that because we're considering both Rob and Sue. Okay. For the standard deduction, that would be whatever B7 is. Okay. And so our standard deduction here is 11,600 for married people filing jointly. So that is what we will record there. Now for the taxable income, we see that we have taxable income for the 0% tax bracket, the 10% tax bracket, 15% tax bracket, and 25% tax bracket. If we look here at the 0% tax bracket, we want to take the the maximum value in between 0 and whatever B17 is minus the sum of B18 and B20 through B20. So B18 through B20 is all of this stuff here, okay? And so when we take our retirement savings, our personal exemptions, and our standard deductions, we're wanting to add all of that because those are the things that we're going to write off or take away from our income here, which is at B17. So basically we're trying to take what's here and we want to subtract from it retirement savings, personal exemptions, and standard deductions. Okay. Now we want the maximum value in between 0 and whatever the difference in between total income minus all of these savings, personal, and standard deduction exemptions that we have. Now, of course, if this expression of B17 minus the sum of B18 and B20, if that was negative, then what we're saying is for the amount of money that they brought in, along with how much they saved to retire, as well as their personal exemptions and standard deductions, by definition of how the government defines these values, the 3,700 for the personal exemption and the 11,600 for the standard deduction, you'll know that those people are in the negative, which effectively means they pay no tax. And so for those people who are, let's say, investors and let's say apartment complexes, this is exactly what they're after. And this is one of the reasons why you have people that are able to be wealthy and not pay taxes, is because they basically use the write-offs for various depreciation and other things to be able to reduce their income that they get, or reduce the sales that they actually get on paper. And it looks like their profit is being reduced, but it's really not. Okay? But anyway, if we move on to the 10% tax rate, then we're taking cell B8, and of course cell B8 is going to be whatever our tax rate is now, which is, in this case, if we look at the 10% tax rate, is 10%. And we're going to do the minimum in between B21 and E8. So B21 is how much taxable income we have in that 0% tax bracket there, okay? And E8, and of course, if we look at E8, E8 is right here, 17,000. So we're trying to find, hey, for the 10% tax rate, give me basically 10% of the smallest number that's in between, what is it, B21, which is our taxable income, and E8, which is the top of the 10% tax bracket, okay? And of course, for the 15% and 25%, everything follows suit there. Now, I want to talk about the 15% rate here for just a second. So this says if you have B21, which is your taxable income rate, if it is greater than E8, so in other words, if it's greater than 17,000, then what we're going to do is put a 0 there, okay? Otherwise, what we're going to do is calculate B9, okay? And of course, our B9 is going to be here. We just moved up to the 15% tax rate then. And then we're going to take the minimum in between B21 and E9, where again, B21 is your taxable income, okay? And E9, if we look here, E9 now is the upper range of the 15% tax rate or tax bracket. And then of course we'll subtract that from whatever E9 is, which is here. And so when we subtract that, we're subtracting away the first 17,000 that someone owes, so that we can get that 15% tax on the remaining amount that's in between the $17,001 and the $69,000. Okay. And of course, the similar kind of thing for the 25% tax rate. If we know that the money that Sue and Rob make is over, in this case, E9, then what we want to do is put 0 in for the tax rate. If not, otherwise, we're going to take B10, which is going to be 0.25 or the 25%, and we want to multiply that by the smallest number in between B21 and E10, okay? Which, of course, B21 again is the taxable income rate, and E10 is going to be the top of the 25% tax rate. So we want the smallest number out of that and subtract from that the first $69,000, so that you only pay the 25% tax on the upper echelon part of your income. Okay. And so, of course, the total tax would just be the sum of everything that is from B22 to B24. And of course, if we're only in the 10% tax bracket, then for cell B22, which is the 15% tax bracket, and cell B24, which is the 25% tax bracket, we'll have zeros there. If we're in the 15% tax bracket, then we'll have a number for 10 and we'll have a number for 15, but we will not have a number for 20 for the 25% tax rate. And of course, at the 25% tax rate, we have basically money that's going to be in all three categories here, okay, for the 10%, 15%, and the 25%. Okay. Now, I know that I've spent a lot of time actually going through the particulars of what Excel is trying to say here, but the reason I wanted to do that is to first get you familiar with some of these functions that they have here, in case you're not familiar with Microsoft Excel at all. So minimum functions, maximum functions, sum functions, if functions are often used. And so want to make sure that you're exposed to this as early as possible. All right, so now that we have all this in Excel, what we want to do is see how this is going to actually turn out. For those of you that are in my course, you actually have a uh, file that actually has this particular example as well as various other examples in it. It's going to be called Unit 1 Examples. And so if you look into your learning assignments area, you'll see that. For those of you that are watching this and you take a course somewhere else, just know that these are PowerPoints that are available. If you send me a message on the YouTube, I could possibly send those too. All right, so now if we use our Microsoft Excel to put in the variables, in this case 55,000 and 50,000 for both Sue and Rob respectively for their incomes, then we see that everything is calculated here, okay? And we see that their total tax for the year is $12,437.50. And since they have to pay taxes quarterly, they need to divide that figure by 4, and that's how they get the $3,109.38. Okay. Now, of course, if we change these numbers, then some of this would actually change. Since they made over $100,000 a year, that's one of the reasons why they were in the 25% tax bracket, because the 25% tax bracket is defined as income who's over $69,000 but less than or equal to $139,350. Okay. All right. So for another example, we're going to look at what we call a break-even example. And so, of course, in business, break-even is just where revenue and cost equal each other. Or if we put it another way, sales and cost end up being the same thing. So normally whenever you have a business or launching a product or whatnot, you're going to have to invest some money into getting that product or business going. And of course, you're going to have to spend that money before you actually start making money. And with that, once you get everything going, whether you have got to get a building, machines, whatever other materials that you need, then of course eventually you come out with your product and you're selling your product. So if you sell your product, then you're going to be getting paid something for it. And at the point where the amount of money that you've made off of selling a product equals the amount of cost that you had to put into it to make that much money off the product in the first place, that is what break-even is. Okay. And so in this example here, we have a clock repair shop, and we're trying to figure out how many of these clocks do we need to repair or whatever so that we are at break-even, meaning that we haven't made any profit, but of course we haven't lost any money either. Okay. And we see here that in particular we're talking about the break-even on repaired springs that we need to get for these watches. And so we know that profit is just going to be the difference in between revenue and cost. So we have this in words here, but at the end of the day, profit is nothing more than the difference in between revenue, which is what sales is, and cost. And that shouldn't be there with an extra S, so I'll just go ahead and erase that. Cost. All right, and so how we actually get revenue is a function of how much you sell times the price you sell it for. And so if we were putting this in variables, it would be X times P, where X is the quantity that you sell, P is the price that you sell it for. And so the way that it's written here is actually written the other way, which is P times X. You have your selling price times the number of units minus whatever your fixed cost is, minus variable cost times the number of units. So whenever we talk about cost, we always know that there are fixed costs and there are variable costs. And so fixed costs are like you have a machine, and let's say you need to put $500 into getting paint in it, calibrating it. Let's say you're making jeans or something, so you may need to load it with buttons and all that. All this stuff costs before you even make one pair of jeans. Okay, so that's what the fixed cost is. The variable cost would be, well, let's say if we're making two types of jeans for our small business here. We have a high-end thick denim type jean, and then we have some cheap jeans. Okay, so of course for the jeans that are relatively cheap, there's not going to be much to it. So there's not going to be many extra things that we need to put on there, and thus the cost of the jean of that particular pair of jeans is just going to be lower than the high-end one, which may have like rhinestones on it, may have some extra stitching, just various things. Okay, so of course, the more stuff you put on it, the more it's going to cost. And so that's what those variable costs are that we're talking about here. And so when we do this, if we actually write it out, we see that cost most times ends up being linear in most cases, where we see that the variable cost per unit is actually what the slope is, the number of units is what x is, and here the fixed cost is what the b is. Okay, and so we're told here that the profit is going to be modeled by this particular equation. So what we're saying here is that to do the repaired springs is going to be $10 per watch or per spring. We have a fixed cost of $1,000, and we also have a fixed cost of $5 per watch. And so from that, knowing that we have to pay basically $5 per watch up front, plus an extra $1,000 to be able to even fix one of these, how many watches or how many repair springs, how many springs we have to repair to be able to break even, meaning our profit is zero. We make no money, but we lose no money. All right, so if we model this, of course, you see that we have selling price, fixed cost, and variable cost. So these are our known variables. Based upon how many units we say that we can sell, we're going to find out from the calculations down here whether our profit is going to be zero or not. In other words, where is our break-even point going to be? Okay, so of course our total revenue is just the amount, which is this here, which is our B9, times B4, which is the selling price per unit. Okay, so how much we sell it for times how many items we sell. That's what revenue is. Our cost, of course, here we have a fixed cost, which is B5, which is 1,000. Our variable cost is going to be the 5 that's here, and B6 times B9, which is how many units we're putting in. And of course, the total cost for that is just going to be fixed cost plus variable cost, or B13 plus B14. And our profit is going to be basically B12, which is our total revenue, minus B15, which is our total cost. And of course, if we're looking for break even, then we want this figure here to end up equaling 0. So if we put in 1,000 units, so if we sell 1,000 units, watches or springs or whatever, then we see that our profit is $4,000 when we do that. Okay, and of course, how we would actually figure out when we would reach a profit of 0, we could use what's called the goal seek function. And so to do that, you'll see that we go to our data tab here, go to what if analysis, and then after that, hit goal seek. And so once we do that, then we have this window that pops up, and basically saying we want to set the cell B16, and let's go back here. Remember what B16 is. This is cell B16. So you want to, in other words, the goal is to get B16 to equal 0 by changing cell B9. So let's go back here. We want this particular cell to be 0 by changing the amount of units that we put into the yellow cell. And that yellow cell is cell B9. Because again, we got B here, 9 there. Okay. So once we set that, then the goal seeker is going to run the numbers and say, all right, well, we'll find out that particular value that's going to make your profit 0. And of course, we see that that ends up being 200 units. Okay, so at 200 units, we neither make money nor do we lose money, and that's what's called our break-even point. All right, so this same example could be expressed another way, and so all I've done here is get a little bit more descriptive on what total cost are in terms of variable cost and fixed cost. I've also talked about revenue, we know profit, and I went here and defined what each of my variables are here: the M, the X, the B, as well as the P, or the price thing. Okay. And again, in this scenario, we pretty much have similar setup, but now we know that we have all of our known parameters here, and we're going to have the number of units there. Okay. And of course, same setup, but the main point of this again is to look here. All right, so another way that we could possibly find out when we have break even is to actually look at a chart like the one that I have here. And so what you see is that for a certain number of units here, we know what the sales are, we know what the variable costs are, we know what's called our contribution margin, we know what the fixed costs are, and total cost. Okay. And so the main thing I want to focus on is these two columns here. So we see that for a certain number of units, we're still in the red, meaning that we're losing money. But if you see, once we get to this point here, so the net income, meaning the amount of money that we bring in, or the revenue, and the net income, so the net income, which is here, yeah, the net income from contribution margin, that's different. Different way of saying the same thing, I should say. But here the net income, which is sales minus total cost, we see that that gets to 0. Okay. And so this is kind of what we're looking for. So here we see that our break even happens at 400 units. And you'll see at 400, if we look down the line here, that's when we have our net income be 0, which is the difference in between revenue and total cost. Okay. All right. So we've talked about how the steps involved in basically coming up with a model. We've seen 2 examples of some simple models where we've used the goal seek function in Microsoft Excel to be able to come up with some type of optimum solution. And so we've done that with taxes, as well as we use the goal seek function to figure out when we're going to be at a break-even point for a company that's selling something. Okay. So now we're going to finish up by talking about some possible problems in actually coming up with these models, as well as we're going to look at an example of doing linear programming by hand. So the examples I gave you actually let Microsoft Excel do everything, but when we talk about linear programming for real, the example I'm going to do by hand is going to give you an idea of how this actually looks and how it works. Okay. So possible problems. So there may be an issue with actually defining what it is that you want to do. It may be so complex that you may think of some things, but you may not think everything. So that's why a lot of times people will get into teams to try to brainstorm to come up with whatever these situations are so you can model them properly. There may be conflicting viewpoints on what is important. Um, if you're doing some type of modeling like this, the results may affect certain departments more adversely than others, or it may benefit some departments more so than others. Of course, when we're defining the problem, we're beginning with some assumptions. So, of course, there are facts, but there are some assumptions that are involved as well. And so we also know that because of that, those assumptions may not necessarily be correct. And also the solutions that we have or the solutions that we want may be outdated. So what worked, let's say, a year ago may not work today. Now, other problems in developing a model, of course, we're doing everything textbook. It's real easy. Everything sort of works out great. But in real life, it's not always like that. We just go through that process of teaching you the textbook way so you at least have some type of foundation to build upon to be able to handle the more complex things in the future. And of course, in the problems that are involved with developing a model is that trying to understand what it's actually doing, okay? And so that's why it's big to really brainstorm, get on teams, and make sure that everyone hashes out everything before you actually start trying to model this mathematically. Now, as far as trying to acquire input, you may be using input that's outdated. You may be using inputs or data that may not necessarily be verified or vetted, okay? And you may not be aware of that. So that's another issue. As far as developing a solution, the mathematics that's involved to be able to model your situation properly may be mathematics beyond your level or any person that's on your team's level. And of course, at that point, you may have to bring in a consultant to help out with that. And of course, the biggest thing is that limitation of only one answer. So whenever we're doing these models, of course, we're going to come up with one answer in most instances. And so the thing with that is that one answer may not be an acceptable answer. You may have a manager that says, hey, I want the 4 or 5 different options I have to be able to maximize profits for my particular product line. And if you're just talking about one option, they may not be able to do that option all the time. So they're kind of pigeonholed in that sense, okay? So to be able to have flexibility of solutions is important, okay? There may be problems with actually testing the solution. The solution may be, so big that it takes a long time to actually run it, okay? Again, the hard to understand mathematics. You may test a solution, but you may not know how to test a solution. If you're not familiar with Microsoft Excel or any other spreadsheet tool, you may be in a situation where testing the solution is a bit difficult for you. Since you're taking this course, we're going to try to do what we can to make sure that at least that part is taken care of. And then, of course, the last problem is once you get your results, actually analyzing the results and interpreting it. One person may interpret the results totally different than the other, and depending upon who's the decision maker and who is not, that may cause a problem as well. So in the implementation process, we know that we may model everything, get a great solution, and then once they see what the results are, some people may be like, well, I don't want to do this because this may, affect my job or affect my position or affect the power and influence that I have, okay? Other people, they're like, well, we don't want to spend a lot of time on this. I have a whole bunch of things to do. Let's just get a quick and dirty solution. And of course, that may work for some instances, but not for all. And of course, the implementation improves with the user and manager involvement. So of course, the more inclusive everyone is, the more they're talking, the more they're communicating, the more everyone understands about what is going on with the model, what needs to be in the model. And so from that point, you get better outcomes and better results in that instance. All right, so to finish up here, we're going to talk about doing a linear programming problem by hand. And so let me going to go ahead and size this correctly so that we can see everything here. So for this problem, we have a manufacturer who makes two types of skis. And one is called a trick ski, one is called a slalom ski. And so for those of you that are skiers, you know the difference in between these two. So the information that we have about manufacturing these skis is the following. So the first thing is that we know that each trick ski requires 6 hours of design work and 1 hour of finishing, okay? So for the trick skis, 6 hours of design, which is basically fabricating it, making it, and then 1 hour of finishing. For the slalom ski, we have 4 hours of designing or fabricating and then 1 hour finishing as well. Okay. The other thing that we're told is that the total number of hours allocated for the design work is 108, and the total available hours for the finishing work is 24. Okay. So that means the total number of hours that this particular business can afford to pay workers to design these trick and slalom skis is going to be a total of 108 hours per whatever production cycle that they're talking about. And then to finish them, which is, basically if it's wood, to sand them down, or plastic, if it's, put the veneer on and all that stuff, will be 24 hours. So now we also know that the final number of trick skis produced must be less than or equal to 15, okay? And so we want to know how many trick skis are we going to allow. So this phrase here, the number of trick skis produced must be less than or equal to 15. That is what we call a constraint, okay? And so with that, we know that we're going to have to consider that here in our solution. So x has to be less than or equal to 15, okay? All right, so let's move on here. So right now, if we were to model this, we know that, of course, using the number of labor hours for the trick ski here will be x, and the number slalom would be y. So actually this needs to go over here. We'll kind of do it this way. So this would be x, and that would be y, okay? And so here we'll have 6x plus 4y is going to be less than or equal to 108, because this is the total amount of hours for the trick ski, total amount of hours for the slalom ski, and now the total number of hours has to be 108 or less. Same thing for the finishing, x plus y less than or equal to 24. And of course, we know that our profits here for this, profit on each trick ski is going to be $5, and the profit for each slalom ski is going to be $10, okay? So we want to know how many of each type of ski should the manufacturer produce to produce the greatest profit, okay? So here we know that in doing this, we're going to have associated lines that go along with these constraints that are here, okay? To make sure that we understand what's going on, when we do our profit function, this is what is called an objective function. Okay, so our objective is to make the most amount of money that we can. Okay, the constraints are, we have fabricating constraints, we have finishing constraints, and we also have a constraint here that says we can't make more than 15 of the trick skis. Okay, so if we look down here, these are what we call inequalities here. And so inequalities themselves have a range of solutions. And so the values of x and y that we actually plug into it, as long as we plug in values of x and y such that this total value here ends up being less than 108, then we're good. And so we want to find the combination of the amount of labor hours for trick skis and slalom skis that will end up being less than or equal to 108. And of course, for the finishing, have that be 24 or less. My point is this. With each inequality, we have an associated line that goes with that. And so I've put those lines there. These lines are in what we call slope intercept. No, not slope intercept, but standard form. Okay. The slope intercept form looks like this. So we could turn these particular lines into slope intercept form, but it's actually better for us to work with them in what we call the general or standard form. Okay, so we're going to graph these lines and kind of see how everything works, and then from the graph here we're going to look at what's called the feasibility region, and from that feasibility region we will be able to figure out what possible values of x and y, those combinations, would be viable solutions. And then we'll look to see what the optimum solution would be. So moving on here. In order to draw this line here, since this particular associated line is in what we call the general form, one of the advantages of having the general form or the standard form of an equation of a line is that we can easily figure out what the x and y intercepts are. If we do that, then we know, well, we can easily draw the line. So I've named this equation 1, named that equation 2. And so here you see for equation 1, if I let x equal 0, then what I'm trying to find is a y-intercept. So if I let x equal 0 right here, then of course this whole term goes away, and now all I have is 4y equals 108. And if I take divide both sides by 4, then I end up with 27 here. Same thing if I plug in 0 for y right here. Let's say, go ahead and erase that, and erase that. If I plug in 0 for y right here, then of course I have that information down here, and you see I end up with x equals 18. So I know that at 0, 27, and at 18, 0, those are my 2 points. So this is the point 0, 27. This is the point 18, 0, and I'm able to draw that line. Okay. So similarly, we have the same thing with equation 2. Of course, plug in 0 for x, get y is 24. Plug in 0 for y, get x is 24. So I have the 2 points 0, 24 and 24, 0, which are here and here respectively. Okay. So now as far as that is concerned, we're good. The one thing that I don't have on here is our constraint equation for inequality for, let me change the colors here for just a second. Change it to here right quick. So we don't have the associated one for x is less than or equal to 15, and that will actually be x equals 15. And of course that would be about right here, and that would be a vertical line that goes through this point here. Okay? And so x equals 15, we notice that because every point that is on a vertical line has the same x coordinate. And so, of course, here this would be 15-0, 15-1, 15-2, 15-3, 15-4, so on and so forth. So we need this extra line in there as well. Okay. All right, so now that we have our associated lines that go with our inequalities, the next thing that we need to do is test those inequality statements to see for what values of x is it going to be true. Okay. And so now that's where we go here. So to find out where our feasibility range is, what we basically do is test each of these inequalities here. And of course, I'm going to add the one about x being less than or equal to 15 here. Normally when we test, we use the point 0, 0 to do our testing. And so we do that because it's an easy point to use. If you ever have an associated line that goes through the origin or goes through the point 0, 0, then you need to pick another point. Okay? And so that's what all this says in here. So now if we go on with our testing, we'll see that for the first one, I'm going to plug in 0 for x and y here. And when I do that, I get 0 is less than or equal to 108. That is true. So since the point 0, 0 is right here, then that means all the points that are on this line and to the left of it will satisfy this particular inequality statement here. If we do the same thing to the x plus y is less than or equal to 24, plug in zeros, we get 0 is less than 24 there. So everything that is on and to the left of that line is also true because the point 0, 0 is right here. We keep on going, then we see for the x is greater than or equal to 0, y is greater than or equal to 0. Of course, we set those constraints in the first place because we can't have negative amount of hours, okay, for the Tricksky or the Shalomsky. So that's why we have that. In addition to that, since this particular associated line is going to be x equals 0, it's going through here. And so if you see we have everything going to the right, and we use the point 1, 1 because the point 0, 0 is right here. So we needed to use something either to the right or to the left of it. I use something to the right. And of course, when I do that, I end up having 1 is greater than or equal to 0, which is a true statement. So all the points that are on the right of this line actually work. Now, similarly speaking, whenever we do y is greater than or equal to 0, we have this associated equation. And of course, if we plug in 1 again for y, using the same point 1, 1 right there, we see that that's a true statement. So y equals 0 is basically the x-axis. And of course, the x-axis always has y coordinates that are 0. So we need everything that's above because the point 1, 1 is above. Okay. All right, and so for the last one, I don't have it on here, but I will draw it, is the line or the inequality here. X is less than or equal to 15. And of course, we'll draw that particular line here. And if we use the point 1, 1 again, so let's say if we use this point 1, 1 again, then of course if I plug in 1 for x, we know that 1 is less than or equal to 15. So everything that is to the left here is actually going to work. Okay. So if we combine all that information together, this is what it's going to look like. And I'm going to add in the actual line x is equal to 15. So I'll do that here. And so now, of course, this is going this way. And so now our feasibility region, and I'm going to correct this here, actually be like this. So our feasibility region will actually be all this here, this here, this here, and then down like that. So it's actually everything that is in this area here. Okay, so that's what our feasibility region would be. Okay, and so now what we would have to do here is basically test our corner points. And so if you notice here, this particular problem has 2 corner points. So if I draw this out like that, my feasibility region kind of looks like this. And so this point and this point are the unknowns, okay? And so if we were working on this, we have to figure out what all these points are. So one of the things that I'm going to do is I'm going to change our problem here to kind of go along with what I originally wanted to do. Is I'm going to ignore the fact of the x has to be less than or equal to 15 here. So I'm going to erase all that just so that the work that I have below actually coincides with everything I was doing here. So I'm just going to come back and erase all of this. But I wanted you to see how, if we would have actually considered that constraint of the trick skis have to be less than or equal to 15, how that would look. Okay. So we'll come back here to the beginning of the problem. And here for this part where it says, finally, the number of trick skis must be less than or equal to 15. We'll just kind of ignore that for now, because I didn't consider that when I first did this problem here. All right, so now that we have all that cleared up here, and we're not considering that other constraint when x is less than or equal to 15, this is what our feasibility region would look like in that case, okay? And from that, we have these corner points. And so these corner points are the outside points that define the feasibility region. And in this case, it would be this point, this one, and this one. And if you notice, we know what all these points are except for this one. And so we need to find that. In order for us to find that, we need to find out where the 2 lines that cross this particular point intersect each other. And so to do that, we would have systems of linear equations here. So I do that down here at the bottom. And so to do that, of course, I'm doing this by what's called the addition or elimination method. I have rules that say if I have 2 equations and I want to change the system here, one thing that I'm able to do is multiply any equation by a non-zero constant and to form a new equation, which is what I have here. I'm also able to add or subtract any of the 2 equations together, and it doesn't change the integrity of the system. So here, when I have this come down here, I'm actually adding these equations together, which means this cancels, and I have 4y minus 6y is a negative 2y, and the difference in between 108 and 144 is a negative 36. And of course, when I solve that, I get y is 18. And then if I use y so I've used this equation to figure it out. Well, actually, I use both of these, but once I have y, I can either use this equation or this one to be able to figure out what x is, and I'm going to use this one because it's easier. So I plug in 18 for y, solve for x, and I get 6. And so now I know that that point that was up here, that's actually the point 618, okay? All right, and so now for us to be able to find out what our optimum solution is, we take these corner points, now that we know what all of them are, and we plug in the various values of x and y into the profit function, or our objective function here. And so, of course, when we plug in x and y into all of them, we see that the largest number that we get here is the 240, okay? So what this tells us is that right now, based upon our current profit model and what we can afford to pay for labor and such, we really need to be in the shalom ski business. We don't need to make trick skis at all. Okay. Now the problem with that is that, of course, if we're a business, we're like, well, no, we make bulk skis, and what happens if the special material for the shalom ski is discontinued, or we have delays on that material? We still need to make money. So don't we have an option to where we could possibly make trick skis? Okay, and that may be the case. Now, let's say we have a situation where, for whatever reason, um, the cost in making a shalom ski has gone up to the point to where our profits have eroded by 50%. And so if we have that, then of course the $10 per ski that was originally here has now dropped to $5. And so now that it's dropped to $5, we want to see what is going to be our new optimum solution here. So if we do the same thing we did last time, we take all of our corner points, which were up here, and plug in the various x and y values into our new profit function. We see now that we have two values, that's 120. And so that goes along with the points 0, 24, and 618. So what this tells us now is that we have two options of being able to achieve maximum profit based upon this new profit model. So we could either make all shalom skis, or we could possibly make 6 trick skis and then just 18 shalom skis. And so we can make the same amount of profit there. Okay. Now, again, this is an example where we're coming up with solutions that provide alternatives to managers or decision makers, because now we have two options instead of one. All right, and so this concludes the very first video for Unit 1 for data-driven decision making. Please let me know if you like this video. If you have any questions on anything, just either, if you're in my course, just communicate with me through those mediums or media. And if you're watching this and you're not in my course and you are interested in giving me some feedback or whatnot, then please leave that on my YouTube page. All right, thanks so much and take care.